Good morning. I am Dr. R. Murali, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bangalore. I am continuing my sessions in the topic partial differential equations in Engineering Mathematics 2 with subject code 15MAT21. Partial differential equations is module 3 in the syllabus. Before we begin our session today, let us recall the topics that were covered in our previous sessions. So, we have seen what is a partial differential equation, or in short a PDE, how to form a PDE by the elimination of arbitrary constants in a given relation, then formation of a PDE by the elimination of arbitrary functions in a relation. We have seen specific examples to illustrate 1 and 2 functions. The same thing was repeated in point number 4 here, where you again eliminated one function, but the formation of the PD was by the elimination of one arbitrary function from a given relation, when the relation is in the form either u equal to f of v or f of u comma v equal to 0, where u and v are functions of x, y and z. And in the previous session, we have seen the solution of non-homogeneous PDEs by a direct integration method. Friends, in today's session, we will be looking into the solution of homogeneous PDEs involving derivatives with respect to one independent variable only. Before we see what such a differential equation is, let us go through our standard notations again. We will consider z to be a function of the independent variables x and y. This is the assumption by default. Maybe in some examples the independent variables may change and also the dependent variable may change, but in general we assume z to be the dependent variable which depends on the variables x and the variable y. So, with these independent variables we have the first order partial derivatives dou z by dou x, also denoted by zx, which is also p, dou z by dou y equal to zy q, dou square z by dou x square, which is zxx, that is r, and dou square z by dou y square, which is zyy, which is t. So, we have excluded this mixed partial derivative because dou square z by dou x dou y is a partial derivative with respect to x and y. It contains both the variables x and y. Today's session, the derivatives will be with respect to only one independent variable. So, we do not consider this derivative. Now, first of all, what is a homogeneous PDE? Now, if each term in a PDE contains either the dependent variable, for example, in our notation the dependent variable was z. So, the PDE should contain only z, or one of its partial derivatives like dou z by dou x, dou z by dou y, dou square z by dou x square and so on, then such PDEs are said to be homogeneous. So, let me repeat again. If each term in a PDE contains either the dependent variable or one of its partial derivatives, the PDE is said to be homogeneous. Otherwise, what was discussed in the previous session, the PDEs become non-homogeneous. Secondly, a solution or integral of a PDE is a relation between the dependent and independent variables that satisfies the given PDE. In today's session, in this section, we consider only homogeneous PDEs involving the derivatives with respect to one independent variable only. Now, if you assume that the dependent variable has been differentiated partially with respect to one independent variable only, say z is differentiated with respect to x only, the PDE can be treated as an ordinary differential equation itself. For example, I have say z equal to x square, right. So, this is z dependent on the variable x. Suppose I differentiate dz by dx, I get 2x. It so happens that dou z by dou x is also equal to 2x. So, these are because these are equivalent, the PDEs with respect to one variable can be treated as an ODE itself. And my friends, I think you are familiar with the solution of a linear differential equation with constant coefficients, which is a ordinary differential equation or ODE. These equations can be either homogeneous or non-homogeneous. For homogeneous equations, we know that the complementary function CF is sufficient and the general solution can be written in the form dependent variable equal to the complementary function. You are used to writing such linear differential equations in terms of dy by dx, y as a function of x containing dy by dx, d square y by dx square and so on. So, for such equations you have seen that the solution is simply y equal to CF, whereas for non-homogeneous equations the solution has two components, one the CF and two the particular integral or PI. For such equations, I think you know friends that the solution, general solution is dependent variable equal to CF plus PI. I repeat again, usually the dependent variable is y dependent on x, so it is y equal to CF plus PI. But the construction of the CF in a linear differential equation with constant coefficients requires an algebraic expression called the auxiliary equation. And you know that in a linear differential equation with constant coefficients, the auxiliary equation can be written by replacing the derivatives in the given differential equation by m. Sometimes you can see that m is also written in terms of capital D, where capital D becomes the differential operator. Now, these things are related to what are called ordinary differential equations, which are either homogeneous or non-homogeneous, linear with constant coefficients. To throw more light on this, let us consider a few examples. For the homogeneous ODE, which is linear, y double dash minus 3y dash plus 2y equal to 0, the auxiliary equation is m square minus 3m plus 2 equal to 0. If you try to compare this with a homogeneous PDE, for example, you take dou square z by dou x square plus z equal to 0, observe clearly that z is dependent variable and it contains only one partial derivative with respect to x. So, it is dou square z by dou x square plus z equal to 0. As we explained in the previous slide, such equations can be considered to be as ODEs also. So, this PDE can be conveniently viewed in the form z double dash plus z equal to 0, which is very much equivalent to the expression for the ODE, so that the auxiliary equation can be written as m square plus 1 equal to 0. Just like you write the AE for y double dash minus 3y dash plus 2y equal to 0, you can write a similar auxiliary equation for z double dash plus z equal to 0 in the form m square plus 1 equal to 0. Again, if you take the equation y double dash plus 2y dash plus y equal to 0, the auxiliary equation will be m square for y double dash, 2m for 2y dash, and for y it is 1. So, m square plus 2m plus 1 equal to 0. Now, if you try to relate this to a homogeneous PDE, so if you consider dou cube z by dou x cube plus 4 dou z by dou x equal to 0, observe the characteristic property of such equations. These equations are homogeneous and the partial derivatives of the dependent variable z will be only with respect to one independent variable. In this case, it is x. So, this equation can be viewed in the form z triple dash plus 4 z dash equal to 0. So, that its auxiliary equation is m cube plus 4m equal to 0. So, m cube for z triple dash, 4m for 4 z dash. Now, friends, I think you have understood the equivalence. Whenever the homogeneous PDE involves the derivative of a single variable, the PDE itself can be viewed as an ODE. So, that the auxiliary equation which you were writing for a ODE can be, the same method can be brought here, and you can construct the AE for such homogeneous partial differential equations. Now, let us come to the method of solution. It is very important that when you solve the problem, you identify the dependent and independent variables. Then write the auxiliary equation by writing the given PDE in its equivalent form. This is necessary because you can easily rewrite the PDE in terms of its auxiliary equation when you write the PDE in terms of its equivalent primes. Then find the roots of the auxiliary equation. You have studied the construction of the complementary function in module 1 and part of it in module 2 also. So, these roots may be real and distinct, or real and equal or coincident, equal roots or imaginary roots, and based on the roots construct the CF or the complementary function. But remember the following when you construct the CF. First, the variable in the CF must be the independent variable. For example, if you have the x as the independent variable, the variable that you write in the CF should be exactly x. If it is y, you write y. Then, like was explained in our previous sessions, since you are in partial differential equations, you do not write constants. The constants in the CF will be replaced by functions of the other independent variable. For example, if your independent variable given in the PDE is x, you write functions of y as constants. And recall that we write constants in the CF of a linear differential equation with constant coefficients. Now, this example will make it more clear. If you consider the homogeneous PDE dou square z by dou x square plus z equal to 0, its equivalence is z double dash plus z equal to 0. So, immediately the auxiliary equation is m square plus 1 equal to 0. So, that the roots of the auxiliary equation are m equal to plus or minus I. So, if you were in an ordinary differential equation, the CF for such roots, if you remember friends, is C1 cos x plus C2 sin x. We retain a similar format, but instead of these constants C1 and C2, you write functions of the other independent variable. So, in this case, because z contains x in the differential equation given, the other independent variable is y. So, instead of C1 and C2, for C1 you write f of y and for C2 you write g of y. So, that the format of the solution remains the same, except that the constants are replaced by functions of the other independent variable. For example, If x is in the given PDE, you write y. If y is in the given PDE, you write x. So, note that instead of the constants C1 and C2, we write functions of y. Therefore, assuming that z is the dependent variable and the independent variables are x and y, point number 1, if the PDE has independent variable x, that is the PDE contains a partial derivative with respect to x, then write CF in the variable x, write the constants as functions of y, and the solution will be dependent variable equal to the CF in the method that was illustrated above. Point number 2, if the PDE has independent variable y, then write the CF in the variable y, write the constants as functions of x, and finally, the solution will be dependent variable equal to complementary function in terms of the independent variable. To illustrate these concepts, let us go to a few examples. In each example, friends, you will see that you will exactly mention what are the dependent and independent variables, so that you can precisely write the solution related to the given PDE. So, in the first example, solve dou square z by dou x square plus z equal to 0, given that x is 0, when x is 0, z is e power y and dou z by dou x equal to 1. So, what do you observe in this equation? First of all, this PDE contains only the dependent variable z and its partial derivatives. So, it is homogeneous. Second, the dependent variable in the PDE is z and the independent variable is x. So, that is specified here. In this example, the dependent variable is x, the independent variable is y, dependent variable is z, I am sorry, the independent variable is x, that you see here. Hence, the constants in the complementary function that is constructed will be functions of y. So, as we have seen earlier, this equation, this PDE can be taken equivalent to z double dash plus z equal to 0, so that the auxiliary equation is m square plus 1 equal to 0, which gives you m square equal to minus 1 or m equal to plus or minus I. Let me repeat again. If you are in an ordinary differential equation which is linear and with constant coefficients, the complementary function for such roots m equal to plus or minus I is C1 cos x plus C2 sin x. But here C1 and C2 are replaced by functions of the other independent variable, which is y. So, that you write CF as f of y cos x, in place of C1 you have f of y plus g of y into sin x. So, what is the required solution? As we explained in our previous slide, the solution to the equation is dependent variable equal to CF, and clearly we said CF should be written in terms of the independent variable. That means these variables x, okay. Complementary function should be written in terms of the independent variable. Here independent variable is x, and the solution to this PDE will be z equal to CF just now written, which is f of y cos x plus g of y into sin x. Now, in many cases when you solve a PDE, along with the PDE, a set of conditions will be specified. If you apply these conditions in the solution and obtain the constants or functions as may be the case, then the corresponding solution becomes a particular solution of the equation. So, in this example, since conditions are specified, you will be able to determine the functions f of y and g of y also, leading you to a particular solution to the given equation. So, how to do that? Start with the solution here, take the solution which you have obtained, apply the conditions step by step. It is given that z is e power y. Let me remind you that the condition in the problem is when x is 0, z is e power y and dou z by dou x equal to 1. So, this independent variable should be applied to both of this. That is to say, you read this as when x is 0, z is e power y, and when x is 0, dou z by dou x equal to 1. So, let us apply the first condition given z equal to e power y when x equal to 0. This you substitute in equation 1. So, left hand side z will be e power y, that you see here. When x is 0, first term cos 0 is 1. The second term you have sin 0 which is 0, which gives you e power y equal to f of y, which is the value of the first function in the solution in 1. Next, apply the second condition which says also from the given data dou z by dou x equal to 1 when x equal to 0. How to do this? You do not have dou z by dou x with you. So, go back to the solution in 1 and differentiate that partially with respect to x. So, from equation 1, dou z by dou x is equal to, differentiate this, cos x is minus sin x. So, you get minus f of y into sin x plus g of y into cos x. This condition you apply the condition dou z by dou x equal to 1 when x equal to 0. So, what happens? The left hand side dou z by dou x will become 1. When you put x equal to 0 in the RHS, sin 0 is 0 and cos 0 is 1. So, this term vanishes, you get just dy, left hand side dou z by dou x value is 1. That gives you the value of gy as 1. So, finally, substitute this constant values calculated in your solution in 1 to get z equal to f of y is e power y into cos x plus gy is 1 into sin x, or z equal to e power y cos x plus sin x becomes the solution. And let me remind you friends, this is a particular solution because you have also determined the functions assumed in the solution to the PDE that you see in equation 1 here. Let us move on to the next example. Solve dou square z by dou y square plus 3 into dou z by dou y minus 4z equal to 0, given that when y is 0, z equal to 1 and dou z by dou y is equal to x. So, what you observe in this? First, this PDE contains the dependent variable z and its partial derivatives with respect to one independent variable which is equal to x. So, you can observe that in this example the dependent variable is z, second the independent variable is y that you see in the partial derivatives here, third hence the constants in the CF will be functions of the variable x. Now, let me throw light in the conditions here. Observe that this is the independent variable. So, this condition has to be read along with both of this. In the sense, you read it as when y is 0, z is 1, and when y is 0, dou z by dou y equal to x. As you remember friends, these conditions can be applied to evaluate or obtain the functions that are assumed in your complementary function. Now, the given PDE, which has now the independent variable y, can be written in terms of primes as z double dash for dou square z by dou y square, z dash for dou z by dou y. So, it is z double dash plus 3 z dash minus 4 z equal to 0. So, what should be the auxiliary equation? As you have seen in the previous examples, z double dash is m square, 3 z dash is 3m, and minus 4 z is minus 4 equal to 0. So, that m square plus 3m minus 4 equal to 0 is the auxiliary equation. On factorization, it gives you m plus 4 into m minus 1 equal to 0, or you have real and distinct roots. Is it correct friends? Real and distinct roots of the form m equal to minus 4 and m equal to 1. Let me recollect again. If these were the roots obtained when you solve a linear differential equation with constant coefficients with y as a function of x, the complementary function would have been written as c1 e power minus 4x plus c2 e power x. What are the changes to be noted here? First, the variable in the CF when you solve a homogeneous PDE should be the independent variable, that is x should be y and this also should be y. That is the first thing to note. Okay. Second, the constants C1 and C2 should be functions of x, because the independent variable is y. So, the CF should contain functions of x as constants. So, what we do, instead of C1 you write f of x into e power minus 4y, do not write x. Remember that you should write only the independent variable in the CF plus g of y into g of x into e power y. Is it clear friends? I have shown the equivalence here. Just rewrite the usual CF in terms of functions of x and in terms of the variable y. Now, once you have the CF, immediately you know that the solution is dependent variable equal to CF, and because in this case the dependent variable is z, the solution to the PDE is z equal to the CF obtained here, which is z equal to f of x e power minus 4y plus g of x e power y. For convenience, we will call that equation 1. Let us apply the first condition. Observe here, when y is 0, z is 1. So, but given z equal to 1 when y equal to 0, apply this condition above. So, what do you get? In place of z in the LHS, you have 1, and in place of y you have 0. So, here e power 0 is 1, the second e power 0 is also equal to 1. So, you get 1 equal to f of x plus g of x. Next, apply the second condition, which is when y equal to 0, dou z by dou y equal to x. That is written here. Also from given data, dou z by dou y is equal to x when y equal to 0. But you cannot go about this condition directly. So, first you must evaluate the value of dou z by dou y from the solution here. So, what is that dou z by dou y? from equation 1 dou z by dou y equal to f of x into, that is a constant, derivative of e power minus 4y is minus 4 e power minus 4y plus g of x constant, derivative of e power y is e power y itself. So, once you finish calculating the derivative dou z by dou y, apply this condition, that is, in place of dou z by dou y you write x and in place of y you write 0, and because e power 0 is 1, it gives you x equal to minus 4 f x plus g of x, and already in equation 1 you have 1 equal to f of x plus g of x. So, just have to solve these equations. So, you already have 1 equal to f of x plus g of x. Solve the equations in 2 and 4, solve them as simultaneous equations. We can illustrate here. You just subtract, when you subtract these two equations, LHS is 1 minus x is equal to gx and gx cancel when you subtract. So, fx minus of minus 4 fx will give 5 into f of x, or fx can be calculated as 1 minus x by 5, that you see here. Then I think you are aware of solving simultaneous equations. Multiply this equation with 4. So, you have 4 and add with this. So, what you get? 4 plus x is equal to 4 f x minus 4 f x will cancel. Here it is 4 g x plus g x, which is 5 into g of x, which gives you g x finally as 4 plus x divided by 5, that is here. So, finally, once you obtain f of x and g of x values, substitute in the solution here in equation 1. So, finally, z equal to f of x is 1 minus x by 5 e power minus 4y plus g of x plus 4 by 5 into e power y becomes the solution of the given PDE. Now, let us illustrate an example with complex roots. In the first example, the real part was 0, but here you will see a root where you have both the real as well as the imaginary parts. So, solve the PDE. Dou square z by dou x square minus 2 dou z by dou x plus 2z equal to 0. Given that this condition, if you observe friends, is given in the reverse direction, that is, you are given first the values of the dependent variable and its derivatives for a condition in terms of x. So, you will read it this way: when x is 0, z is e power y. Similarly, when x is 0, dou z by dou x equal to 1. So, before you start solving this example, observe the following. First, this PDE contains the dependent variable as z. Second, the independent variable is x. So, remember, you should write complementary function in terms of x, and the constants in the CF will be replaced by functions of y. So, the PDE in its equivalent form is z double dash for dou square z by dou x square, z dash for dou z by dou x. So, it is z double dash minus 2z dash plus 2z equal to 0, and the auxiliary equation is m square minus 2m plus 2 equal to 0, which is not factorizable. So, apply the standard formula minus b plus or minus square root of b square minus 4ac by 2a. So, you get m as 2 plus or minus root 4 minus 8 by 2, which is 2 plus or minus 2i by 2, or if you cancel 2 throughout, you get 1 plus or minus I. Again, if you were in a linear differential equation with constant coefficients and I get such roots, recall friends that the CF was like this, e power x into C1 cos x plus C2 sin x. But in homogeneous PDEs, remember the following changes. First, the variable in the CF should be the independent variable. Of course, here x is the independent variable. So, you retain the same variable x and also this x, but the constant C1 and C2 should be functions of y. Is it clear? So, you write e power x into f of y into cos x plus g of y into sin x. So, that the solution to the PDE is z equal to e power x into f of y into cos x plus g of y into sin x. Now, let us calculate the constants f of y and g of y. First, observe that from the given data, z is e power y when x is equal to 0. You have this condition here. So, apply this in equation 1. In place of z, you write e power y, hence equation 1 becomes e power y. Here cos 0 is 1, e power 0 is also 1. Okay. So, you get 1 into f of y into 1 plus sin 0 is 0, which immediately gives you the first function in the solution, f of y as e power y. Again by data, dou z by dou x is 1 when x equal to 0. How to apply this? First, calculate dou z by dou x from the solution in 1, differentiate this partially with respect to x, and because it contains two functions of x, this and this, you need to apply the product rule. So, on differentiation, dou z by dou x will be e power x into derivative of f of y cos x plus g of y into sin x is minus f of y into sin x plus g of y into cos x plus second function f of y cos x plus g of y into sin x into the differentiation of e power x, which is e power x itself. Now, apply this condition to the derivative. So, in place of dou z by dou x, you write 1, in place of x you write 0, because x is 0, these values will be 0, because sin 0 is 0, e power 0 is 1. So, this is 1, this is 1, cos 0 is 1. So, you are left with left hand side dou z by dou x 1 equal to g of y here plus f of y here. But observe that you already know f of y here. So, since f of y is e power y, it follows that g of y is immediately 1 minus f of y or 1 minus e to the power of y. Okay? So, but since f of y is e power y, so immediately you get this. Substitute the f of y obtained, which is e power y, and the g of y obtained just now in equation 1 here for the required solution to the PDE, which is z equal to e power x into e power y cos x plus 1 minus e power y into sin x. We will move on to the next example. Solve dou square u by dou x square equal to a square into u, satisfying the conditions u equal to 0 and ux equal to a sin y when x equal to 0. So, what are the observations to be made? First, in this example, the dependent variable is u, not z. Okay? Keep this in mind, it is u and not z. Second, the independent variable is x, you can see the partial derivative with respect to x. Third, the constants in the CF will be functions of y, but the fourth very important. Note that the terms containing u or the independent variable in general must be in the LHS only, that is in the given equation, because RHS contains the term a square into u. This a square into u should go to LHS only because it contains the dependent variable. So, the given PDE, which is dou square u by dou x square equal to a square u, can be written as dou square u by dou x square minus a square u equal to 0. Its equivalence in terms of the prime notation is u double dash for dou square u by dou x square minus a square u equal to 0. The auxiliary equation is m square minus a square equal to 0, which gives you m square equal to a square, or on solving you get the roots as m equal to plus or minus a. So, let me repeat again, for a and minus a, it is c1 e power ax plus c2 e power minus ax in the normal sense. But since you are in a PDE, you write the independent variable here in terms here, but here in this problem, because the independent variable is x, you retain the same thing, and instead of the constant c1 c2, you will write functions of y. So, that complementary function is f of y e power ax plus g of y into e power minus ax. So, that the solution to the PDE is u equal to f of y e power ax plus g of y into e power minus ax. Let us call that equation 1. Apply the first condition. It is given that u is 0 when x is 0. Substitute here. You get 0 equal to f of y e power 0 plus g of y e power 0. E power 0 being 1, you get 0 equal to f of y plus g of y. Also from the data, dou u by dou x, we introduced the notations in the beginning of the session. Dou u by dou x is same as ux, is a sin y when x equal to 0. But as you know friends, you cannot apply this directly. So, you have to go to equation 1 here and first calculate dou u by dou x or ux, which is f of y into a e power ax for e power ax plus g of y into minus a e power minus ax for this. So, that finally, ux is a f of y e power ax minus a g of y e power minus ax. Now, apply the second condition given here, which is ux is a sin y when x is 0. So, left hand side ux becomes a sin y here, and in the right side you put x equal to 0. So, that will give you a sin y equal to a into f of y minus a into g of y, which you see here. E power 0 and e power 0 here are both 1. Left hand side you have a sin y. So, you can cancel a throughout to get sin y equal to f y minus g of y. But your equation 2 here is 0 equal to f of y plus g of y. So, take both of these equations and solve these equations simultaneously. So, solving these equations, add them, you get sin y plus 0, sin y equal to 2 fy or fy equal to sin y by 2, subtract them. So, sin y minus 0, which is sin y, fy cancels, you get minus gy which is minus 2 gy, or gy will be minus sin y divided by 2. Substitute these expressions in the solution here that was earlier obtained as equation 1. So, that u equal to sin y by 2 for fx e power ax minus sin y by 2 e power minus ax, this is for gx, or again you have sin y common. If you take that out, you get sin y by 2 into e power ax minus e power minus ax. But it is known that this expression e power ax minus e power minus ax is 2 sin hyperbolic ax. So, that if you finally cancel the 2, you are left with u equal to sin y sin hyperbolic ax as the solution to the given partial differential equation. We will now solve a similar example where the dependent variable is z and the independent variable is y. So, solve zyy plus 9z equal to 0, satisfying the condition z x comma 0 equal to 0, sorry, equal to e square. Remember that you have assumed z as a function of x and y. So, z of x comma 0 means when y is 0, there is no change in x. When y is 0, z is e square, and when y is 0, zy, which is dou z by dou y, is equal to minus 1. So, the dependent variable is z, independent variable is y. The constants in the CF should be functions of x. So, the equivalence of the given problem is z double dash plus 9z equal to 0 with AE m square plus 9, which gives you m equal to plus or minus 3i. So, if you assume functions of x as constants, the complementary function is f of x into cos 3y plus g of x into sin 3y. So, that the solution to the PDE is z equal to f of x cos 3y plus g of x sin 3y. Let us apply the conditions, but it is given that z x 0 equal to e square, which means when y is 0, z is e square, substitute that here. So, z will be e square in the LHS. When y is 0, cos 0 is 1, sin 0 is 0. So, this term cancels, this term vanishes. So, you get e square equal to f of x. This gives you the first arbitrary function. Second, given zy x 0 equal to minus 1, which means when y is 0, the partial derivative of z with respect to y is minus 1. To apply this condition, first obtain zy from equation 1 by differentiating partially with respect to y. So, you get zy as minus 3 fx sin 3y plus 3 gx cos 3y. So, when you apply this condition, zy becomes minus 1, sin 0 is 0 because y is 0, cos 0 is 1. So, this term vanishes, you get this term equal to 1. So, you get zy minus 1 equal to 3 gx or gx equal to minus 1 by 3. Now, finally, substitute fx and gx values obtained in equation 1 here to obtain the solution as z equal to e square cos 3y minus 1 by 3 into sin 3y. One more example. In this example, observe that you have the third order partial derivative dou cube z by dou x cube plus 4 dou z by dou x equal to 0. Given when x is 0, z is 0, zx is also 0, z double x is equal to minus 2. The equivalence of this PDE is z triple dash plus 4 z dash equal to 0. So, the auxiliary equation is m cube plus 4m, which is m into m square plus 4 equal to 0, or m equal to 0 and plus or minus 2y. So, that the complementary function for 0 it is f of y e power 0 into x, which is 1. For plus or minus 2y, you would assume the function gy cos 2x plus h of y into sin 2x. So, that the solution to the PDE is z equal to fy plus gy cos 2x plus hy sin 2x, but by data z is 0 when x is 0. So, substitute that here. So, 0 will be sin 0 will be 0, you get f of y plus g of y. Also, zx is 0 when x is 0. To apply this, first find zx from this. Zx is 0 here, minus 2 sin 2x into g of y plus 2 cos 2x into h of y. So, when you apply this condition, when x is 0, left hand side zx will be 0, sin 0 is 0 here, cos 0 is 1. So, you get 0 equal to 2 hy or hy equal to 0. Finally, apply the condition zxx equal to minus 2 when x equal to 0. For this, you should differentiate this again with respect to x to get zxx as minus 4 gy cos 2x minus 4 hy into sin 2x. Apply the condition zxx is minus 2 when x is 0, when x is 0, sin 0 is 0, cos 0 is 1. So, immediately from this you get minus 2 equal to minus 4 gy or gy equal to half. Hence, you have the relations f of y plus g of y equal to 0 obtained from the previous slide here. Then h of y 0 and g of y equal to half. Substitute gy obtained here in this equation to get f of y equal to minus half. So, that you have f of y as minus half, gy as half and hy as 0. So, that when you substitute in equation 1, which is this equation, we have written the equation again here. You get the solution as f of y minus half plus g of y is half into cos 2x. If you take minus half outside, you get 1 minus cos 2x, and 1 minus cos 2x is known to be 2 sin square x. So, that if you cancel 2 finally, the solution becomes z equal to minus sin square x. So, friends, in today's session, we have seen what is a homogeneous partial differential equation, in which the derivatives present will be with respect to one independent variable and their solutions. Thank you.